So the proximity effect is why the 1,2 product is always the kinetic product, and we can prove this because in this reaction, our carbons that are our 1 through 4 carbons for our conjugated diene are not from 1,4-butadiene or 1,3-butadiene, they are from 1,3-pentadiene. So that both of the carbons that contain the positive charge are secondary, and so they are both secondary allylic cations. And so we can show that the stability of the cation is not why the 1,2 product is the kinetic product, because when we perform the reaction with 1,3-pentadiene, the 1,2 product, or the fastest form product, is still in cold conditions is still 78% favored over the 1,4 product. So when the cations are equal, the 1,2 product is still formed faster, and it has nothing to do with having a partial positive charge on a secondary carbon. It has to do with the proximity of chloride to carbon 2 once the hydrogen or deuterium bonds at carbon 1. Okay, looking at other kinetic and thermodynamic products, we have 4-methyl-1,3-pentadiene. And this is a case, I was telling you that the 1,2 product will always be the kinetic product, and it will sometimes be the thermodynamic product, and that sometimes the 1,4 product will be the thermodynamic product. And we're going to determine what is the thermodynamic product based on the substitution of the pi bond. So for the 1,3-pentadiene, we should draw our cation. So how do we decide? Again, remember, how do you decide if this is carbon 1 of the diene, if the yellow carbon is carbon 1 of the diene, or if the blue carbon is carbon 1 of the diene? And that has to do with what is the most stable position for the first cation, for the 1,2 cation. So the most stable position for the 1,2 cation, I'm going to, well, yellow is not really good. Okay, I'm going to change the highlight color. Highlighter, let's go with green because the green pen is more visible. All right, so we have our 2 carbons, and we're trying to figure out which one is going to be the more stable cation. Really? And so I'm going to draw the green cation. Do we end up with the hydrogen adding at the green carbon? Ooh, not a positive charge, not a double bond. Okay, single bond, CH, positive charge, CH, double bond, C, methyl group. Methyl group. So which is the most stable? Is it the green or the blue that gains a hydrogen? And those 2 cations are equally stable. They're both secondary allylic cations. Okay, but the pi bond is not equally stable. And so it turns out that the green is going to be the best position to add hydrogen at the beginning, because if you determine that the position for the positive charge is equal, then you can determine whether the green carbon or the blue carbon adds hydrogen by looking at the pi bond. The most stable position for the pi bond is the second thing to consider after considering cation. So first consider cation. And then second, consider pi bond. And if you can answer when you look at the cation, you can already answer the question, then you don't have to consider the pi bond. Okay, and this is for choosing where H adds. Or that initial electrophile adds. Okay, so next, once we know that the green cation is how things are going to go, then I don't need the blue cation anymore. I can get rid of it. And I can go in and take my green cation and draw the two possible cations, the 1,2 cation, which will give us the 1,2 product. And that's the same cation that we've already drawn. Okay, drawing it incorrectly. I feel the incorrectness of it. CH, then a second CH, double bond C with a methyl group, two methyl groups. One here and one here. Okay, so there's our 1,2 cation. And this has a tri-substituted double bond. And then we can draw our 1,4 cation. I might use a darker green. And the 1,4 cation is going to have the pi bond moved from carbon 3, between carbon 3 and 4 to between carbon 2 and 3. And that's going to move that the positive charge is now on this tertiary carbon. But when we're choosing the thermodynamic product, we only consider the pi bond. We ignore the cation. I may write that in a different color. Okay, so only consider pi position. So that means that we're looking for the substitution. The 1,2 cation is tri-substituted. The 1,4 cation is di-substituted. Tri-substituted is better than di-substituted, and so the 1,2 product is the thermodynamic product. So the 1,2 product then is both kinetic and thermodynamic. Okay, kinetic and thermodynamic products. We know that the 1,2 product is always the kinetic product, and then you have to evaluate, do we actually have a thermodynamic? We may not even have a thermodynamic product because they may be equally stable. So we have a disubstituted and a disubstituted pi bond, then they neither one is the thermodynamic product, they're both the thermodynamic product. And in the thermodynamic reaction, you'll make both of them. Ooh, this is a new topic. I'm going to start Diels-Alder reactions on the next video.